Great. Well, thanks for having me. You've gone to great lengths to prevent me from coming to headquarters, but I hope everybody's safe and that the next edition of the next episode of this science fiction movie is better than this one. So I'm going to talk about this paper, statistically valid inferences from privacy protected data. It's with where are we here? Yeah, it's with Georgie and Meg, who are my graduate students. Meg, at the moment, is taking a leave. She's Joe Biden's chief data scientist, and with the one and only Aberdeep, who maybe you have heard of. I'm happy to be interrupted. I don't know if Google Meet has chat, but if you want to just speak and interrupt, that's totally fine. I'm going to talk about solving political problems technologically, differential privacy, and inferential validity, which is often left off when you talk about differential privacy, but is essential. And then a particular algorithm we came up with to put both of them together, and I'll show you how it works in practice. The big picture is that I'm a social scientist. Social scientists have more data than ever before. And that has enabled spectacular discoveries. But even though we have more data than ever before, we have a smaller fraction of data in the world than ever before, because most of it's locked up inside governments and private companies and others. And similarly, those like you in companies have more data than ever before, but there's quite a lot of data that you don't have access to, which if you did from your customers or from other parts of the business to which you don't have access, or from your partners out there in the commercial world, if there was appropriate ways of you getting it, it would empower private industry, academia, public good, all kinds of things. So I want to work on, and we're working on basically technological solutions to political problems. So I'm going to describe one that is a constitutional solution to a political problem, and then we'll talk about a technical one, which will be differential privacy. Okay, so I'm going to tell the story about how I got into this, which was trying to convince Facebook to make data available to academics for research. And as I said, this is also solving political problems technologically. So I'm out visiting Facebook, and I've visited them lots of times before over a lot of years, trying to convince them to make data available. It doesn't usually go well, but it was worth a try. And I'm in my hotel room packing to go home, and I get an email from the people I was talking to at Facebook, and they say, hey, what do we do about this? And this was Cambridge Analytica. So this was the worst timed lobby event in the history of the world. Right? It was crazy, right? Like, because Cambridge Analytica was an academic that violated his responsibility and gave the data to some private company. So that didn't make any sense. So I went home, I packed, I thought, there's enough of this. And so I get a call 3 days later from Mark Zuckerberg, who said, hey, could you do a study of the 2016 election and implicitly and tell everybody that we didn't change the outcome, or if we did change the outcome, tell us what to do, we'll do it right away, right? Because, losing $100 billion sort of focuses the mind. And so I thought about it, and I said, oh, I'd love to do that study. I'd love to have access to the information to do that study, but I need two things, and you're really only going to give me one thing if you think about it, right? And he said, well, what are those two things? I said, the two things are, first of all, complete access to the people and the processes and the platform and the data, just like you give employees. Of course, I'd need all that to do the study, but I need a second thing in order for the study to be reputable. I need no pre-publication approval by the company. Employees don't get that, of course, right? You sign agreements so that before you publish anything, it goes to the comms team. They make a decision about whether it's public. Of course, that makes sense. But if that were a requirement for me as an outside academic, then even if I could publish it, because you let me publish it, it would be of no value to the academic community. So I said I need both of those things. And he said, well, so you need both of those things. I can't give you both of those things. And I said, okay, that's fine. I'm not going to do the study. He said, no, I still want you to do the study. And I said, well, okay, give me both of those things. He said, no, I can't give you both of those things. And I said, well, I'm not going to do, so we went back and forth until finally I realized a solution. Instead of giving me those two things, we create two groups and you give each group one. So here's the two-part solution. And this is the constitutional solution. The first group are outside academics that propose to study specific topics with no company veto whatsoever, no pre-publication approval. It's legitimate to have them study specific topics because outside academics, when they apply for access to government data and all kinds of other things, they have to say what they're going to study. So that's no problem. But the key thing here is Facebook doesn't decide who gets the data access. Instead, we set up a trusted third party that understands the inside issues at Facebook and understands the issues and stands up for academics as well. It was a commission of senior distinguished academics at a little organization I set up called Social Science One. You can see socialscience.one. They sign NDAs. They take one for the team and agree not to publish anything on the basis of this because they have all this inside information from Facebook. They choose data sets, they make final decisions, and they can report publicly if Facebook reneges on its bargain. And the key thing is that they have that freedom, so that they're really a trusted third party, but they really understand what's going on inside Facebook. So if there's some lawsuit that nobody knows about that is on a topic that somebody proposed to study, and that study was going to be a great study, we would disallow it because of this private information that we would have. So that's great. Problem solved. No balancing of privacy versus anything else, or the needs of one versus everybody got 100% of what they wanted. There were agreements signed, legal agreements signed, announcements. Mark Zuckerberg testified before Congress and discussed this. There was funding from outside foundations. 30+ people signed at Facebook, and now actually quite a lot more. There was just one issue, which is the particular scheme that Facebook had to implement all of this was, well, it was illegal, and so that wouldn't work. Okay, and so what do we do, right? Like they didn't know it was illegal, of course, right? Like we all discovered this along the way, but it couldn't work. Like the regulator said, there's no way that you're going to be able to do this. It doesn't make any sense. So we solved one political problem technologically, but now we had another problem. And we have to figure out how to take data and make it leave Facebook without it leaving Facebook. And so this is where differential privacy comes in, and we basically introduced it to the folks there and figured out how to use it in a productive way. So the way I think about it, just to give you this framework, is that there's a data sharing regime which we're going to switch to a data access regime. The data sharing regime is what we, the social scientists, have always lived under. It's another solution to a political problem via technological means. So the data sharing regime is, I give you data, maybe you sign a DUA, that's the whole thing. Then there's a data access regime. So let me just go back to the first one. So this data sharing regime, as you probably well know, it goes back a century, but is failing. There's increasing public concern about privacy. Scholars have discovered that de-identification, all it does is take off the names, but it doesn't actually make it impossible to re-identify. Actually, it's quite easy to re-identify people. De-identification doesn't work, nor do all these other methods of that basically demonstrate that we tried hard to protect people's privacy, but that's different than guaranteeing that you're going to protect their privacy. And and of course, trusting researchers fails spectacularly at times. That's what Cambridge Analytica was. There's even a great paper called the Feinberg problem that shows that even trusting a researcher who is known to be trustworthy can fail to protect people's privacy. So that's sort of a bummer. So we think that this is going to change from right now. Academics and among themselves and with companies and with governments and nonprofits are sharing data under this data sharing regime. And I think instead we're going to provide access to data on a server. We're going to share a server spun up and defined in exactly the way we want. And so the idea is this trusted server holds the data. The researchers are treated as adversaries, which, just so you know, pisses me off to no end. Okay. the researchers can run any statistical method they want. That's really important, okay? Otherwise, we don't have them on board either. So we have to enable them to do whatever they want. And they get an answer that is more uncertain than it would be otherwise, but still has good statistical properties. That's the idea. So a noisy answer. They can only run it a limited number of times because of the privacy budget. The goal is to make it, the goal, not necessarily achieved, but the goal is to make it impossible to violate individual privacy, but possible to discover population level patterns. Since I'm a social scientist, like people in public health and elsewhere, I don't care about anybody. I only care about everybody, right? We care about societal level patterns, not anybody's individual information. And that, roughly speaking, is differential privacy. And that, in my experience with Facebook, actually does seem to satisfy regulators around the world, which is really great. However, that leads to a new problem. Most differentially private algorithms are statistically invalid. Okay, that means, so what do I mean by that? That means the statistical properties, which I'll explain, are usually unknown, and when we analyze them, they're usually biased. They will give the wrong answer to the kinds of questions that we have about the data. And of course, they don't come with any uncertainty estimates. And so you can't make a scientific statement. A scientific statement is not one that is necessarily correct. It is one that comes with known statistical properties and has accurate uncertainty estimates. So you can't make if you can't make scientific statements, what's the point exactly? You've protected people's privacy, but you might as well protect it by just not giving away the data. Okay, so let me describe that in somewhat more detail and more by differential privacy and inferential validity. So I want to contrast two theories of inference. Inference is just, the definition of inference to me is using data you have to learn about data you don't have. That's, or using facts you have to learn about facts you don't have. That's inference. But statistics and computer science, it seems, have fundamentally different theories of inference. And this is actually really important. So let's take a population of people. So I have a whole bunch of people there. Aberdeep's always hard to hide in the population, so I put them in there. But in any event, suppose there's our quantity of interest, let's suppose, is the average income, let's say $48,000 of the entire population of people. Okay, and then we have a sample. Now, a sample to a statistician it needs to be defined with considerable precision. It could be a simple random sample, a blocked random sample, a stratified random sample, a haphazard sample, whatever it is. We have to know exactly what the data generation process is. That's what the sample is. And then once we have a sample, we get data on only the people in the sample and not any of these people at the top, which are millions of others, presumably. The key thing here is each one of there's a bunch of numbers here, and here's the mean of the sample. The mean of that sample is basically irrelevant for most practical purposes. And that's because the thing that we care about is the mean in the population as statisticians, as social scientists. We don't care about the mean of the sample. If you ask a random sample of Americans, who are you going to vote for in the next election? The answers just don't matter at all. Right, 90% of people don't answer that particular survey question, and so you have to do all kinds of adjustments to make a proper inference back to the population. And so the answers you get to the questions and the average you get from the answers just don't matter. It's how you use the data generation process to get from this column back to this column. That's the key. That's inference. That's what statisticians do. Okay, so now let's talk about the computer science model. Computer science model is usually we have this database, and we do a query, and we get an answer. So we say, for most purposes, not all purposes, but for most purposes, it's I want to know what the mean in the database is. Give me the mean, and you send that to the database, and it gives you back the mean. Of course, computer scientists are also interested in a vast array of other things, and sometimes it's prediction, which is, of course, an inference out of sample, and sometimes it's classification of new data or images or whatever it is coming into your database, so it's other things. But roughly speaking, it's the query response model of inference. Okay, now let's suppose this database is private. If it's private, well, it turns red and gets embarrassed. Okay, so that's a pre-programmed joke. And then we're going to protect it with differential privacy, and the way to do that is you add noise and censoring. So in the CS literature, they call it clamping sometimes, or things like that. But in statistics, that's censoring. You take a number that's larger than a certain value and you bring it back down to that value. Or if it's too negative, you bring it into that value. We call that censoring. And then, of course, we get, after adding noise and censoring, we get a bunch of different numbers. Now, obviously, the mean of these numbers has no meaning at all, no meaning in and of itself at all, of course. But we're interested, from this theory of inference, to use that number to infer back to the database, to the private database that we don't have. And we use this data generation process instead of this one to infer from this column to this column. That's the basic, everybody follow me? Right? Okay, but now from a statistical point of view, or a social science point of view, what we see is this column. What we care about is this column. What we do not care about is anything in the middle. Although, of course, the things in this data generation process and this data generation process are what constitute information we will use to start with this column and make an inference all the way to this column. So this is really what we want to do. And notice I have the entire title of the paper in here. Isn't that cool? And I drew those arrows in LaTeX. Isn't that really neat?
Gary, so it's one tiny point. I don't know if you're moving a mouse around or pointing, but like we don't see a pointer. So when you say this column or that column, we are running to figure out what you're talking about.
Can you see this? Can you see this?
Yes, it's better.
Apologies. Meet works differently than Zoom.
Yeah.
Apologies.
I know all the hide stuff at the bottom, but yeah.
Okay. Anyway, maybe you. So these are the data generation processes. Yeah. This one for statistics. This one for differential privacy. We really want to go from this column all the way to this column, which is this nice last thing here. Yeah. Okay. All right. Let's make that thing go away. Can you see that little panel on the bottom when that appears? No.
No.
Okay, good. Okay, so I'll just do it this way. Okay. Differential privacy and its inferential challenges. The estimators, the way to think about it in classical statistics is we have an estimator as a function of the data. So S is the statistic. I always tell students that the etymology of the word statistics comes from sample characteristics, and that's a lie, by the way. It's totally wrong, but lying is an excellent method of teaching. That's another joke. That's actually true and a joke. But in any event, this is a statistic, a function of the data set D. We then, in differential privacy, we typically have some kind of mechanism, which is another function of the data, but where noise and censoring are part of it. The key thing, though, is noise and censoring. They're essential components of ensuring privacy, but they're fundamental problems for statistical inference. So the differential privacy standard, which I'm going to show you now, but I find over time that the first time I give a talk, it's filled with math. And the second time I realize I can simplify it. And the third time I can simplify it more. And and by the end, I can almost do the entire talk without math. So there's going to be math here, but I'm going to simplify as much as possible just to clarify the points. And so here's the simplest version I could come up with of the differential privacy standard. All of this is probably transparent to you guys. There's a data set D with your information and a data set D prime without your information. And the standard for small values of epsilon is that the probability that the mechanism produces a value M as a function of D is almost the same as the value of that mechanism given D prime. That the probability of producing the same M is the same, or it's within epsilon of 1. And as long as epsilon is small, this actually is a correct approximation to the real definition of differential privacy. And that's true for all D and all D prime and all M. And this definition excludes all random variability due to inference to the population. So that's an important point. So that means that we have to add on inferential validity over and above to whatever the differential. If you demonstrate that a result is differentially private, you have another step to go. Not to protect privacy, but to make it inferentially valid. Okay, so let me give you a key example here. This example is a very simple example, but we will use it. So this is a differentially private mean. And the way that it works is we first take a mean, not of the outcome variable y, but a censored value of y. That's what the C function is. So lambda is an arbitrarily chosen value that we're going to clamp or censor at. Anything larger than that gets moved down to that value. So you censor it and then take the mean of the censored values, and then this is noise added on at the end. If you're wondering where I got this 8 from in these numbers, I took approximate differential privacy, which maybe you're all familiar with, and I chose a delta to make this a nice round number. And since no one has any reason to choose one delta rather than another, I'm going with the simple version. In any event, so lambda has this sort of horrible Heisenberg property where you want lambda here to be really large so that there's no censoring. But it's also here, and if it's large, then there's a lot of noise. So either you get a lot of bias from a statistical point of view, or you get a lot of inefficiency from a statistical point of view. And it's sort of your choice. Fortunately, n is in the denominator here, so the noise is reduced the more observations you have, because you can submerge anybody's data in a sea of others. That's great, but the more privacy you have, the more privacy you have to ensure, the more noise is added at the end as well. Of course, there's lots of other things people do. They mess with the gradients, like, oh my gosh, to figure out how to deal with that statistically. Like, I mean, I understand that we clip the gradients in order to make, as a sort of ad hoc way to regularize predictions and things like that. But figuring out how to correct that when you haven't even gotten to the optimum, I don't know. But it's really important that we figure that out. If our quantities of interest are things like causal effects, rather than, or means or descriptive statistics, rather than predictions. Anyway, they also change like in regression, change the X prime X matrix, or you can change the data, you can change the quantities of interest. There's lots of other possibilities. The statistical properties of all these things, I think you can see, are usually biased. There's no uncertainty estimates, and so we're going to have to do something. Okay, so the properties of differential privacy that we're going to use here, the first one is post-processing. So if a mechanism is differentially private, so is any function of the mechanism that doesn't include the private data. So that's great. That's really useful for bias correction. So we will bias correct after the fact, very often anyway. The privacy risk is quantified as epsilon rather than just 0 or 1 for whether we tried hard to re-identify. That's helpful mathematically, but it's pretty insufficient in applications because nobody really knows what to set epsilon at. And in real applications of differential privacy, epsilon's set to numbers large enough so that if you go back to the definition of differential privacy, you say, what's going on exactly? Right? It's like that number 1 plus, let's say, 1. Right? That's not really bounding it very much. But of course, the reason is that differential privacy is about the maximum privacy loss, not the actual or real privacy loss. And one is orders of magnitude larger than the other in most situations. So basically, differential privacy gives us the worst case scenario. That's the definition. It's good that that's the definition, but it's often unhelpful in practice. And I give these 2 points here because I think we need some more research to really figure them out, to figure out how to bring this to practice. Right now we do what's intuitive, and it's not wrong, but it's clearly not analyzed in a full way. There's a privacy budget, so there's composition. I think we can limit the maximum risks across analysis and researchers if we have that budget by applying the composition theorems. When the budget is used up, however, no new analyses can ever be run. For statisticians, for data scientists, for social scientists, that is a big deal. That completely changes statistical best practices. So everything we learned about how to do data science completely changes. This is really important to the people using the results of the data. And if you don't pay attention to this, you get the wrong answer, okay? Random noise does not come out in the wash. Okay, it may be on average correct for one number, but even if you're estimating something as simple as a regression coefficient, the bias is in unpredictable directions if you have two explanatory variables or more. It could be too big, it could be too small, the sign could be different, et cetera. Anyway, without differential privacy, we balance worries. And there's two worries. One worry is p-hacking. We worry about the researcher. The researcher might try so hard to get their result that they tweak the regression, they tweak the analyses until they get the results, and they have proof that it is possible to find results consistent with their hypothesis rather than demonstrating the veracity of their results. So that's p-hacking. That's one worry. A second worry are all the usual threats to inference: omitted variable bias, measurement error, missing data, lots and lots of things. For p-hacking, the solution is doing things ex ante, before the fact, like pre-registration. We make pharmaceutical companies pre-register their data so they don't run 30 experiments and only report publicly the one that's significant. Think of it like if we were tasked with coming up with a Mars lander, we have one shot, right? We don't get to try it, see if it works, try another, see it works. Each one of these is like several $1 billion, right? So you put everything into the ex ante work. That's how you deal with p-hacking. You tie your hands, basically. Well, what about threats to inference? Well, the way you deal with threats to inference is ex post. Ex post, you're encouraged as a data analyst to do every possible diagnosis and exploration and serendipity and all kinds of things after the fact, right? Serendipity is to discover things, of course. And observational data, like surveys, that's how we analyze. That's how we're taught to analyze things, by putting in tremendous effort after the fact. With differential privacy, p-hacking, very interestingly, is mostly taken care of. There's some good papers that show that you can't overfit, for example, if the data points themselves are like jittering around like little quantum objects, right? Because they've got noise added to them. So p-hacking is pretty much taken care of. However, you have to treat observational data like surveys like a Mars lander project. Since you can run a limited number of analyses, you can't and shouldn't run every possible exploration and diagnosis you can. You have to think entirely ahead of time. So it could totally change. It takes all the people that have been doing ex post analyses and makes them into people that were doing ex ante analysis. So it really changes things, and we have to worry about that. Okay, so here's an algorithm that the four of us came up with that is statistically valid, and it is general purpose, which means that you can run almost any statistical procedure and estimate almost any quantity of interest within this. It will be differentially private, and it will be statistically valid, by which I mean it will be approximately unbiased, and we will have appropriate uncertainty estimates. So here, this is follows the central or global model of differential privacy, where you make a query to a server. We have written other papers in which sometimes differential privacy is done by adding noise to a data set, and then we analyze the data set. Those are different statistical methods. We've done a paper on analyzing survey data, which does it in a bunch of different ways. Those are yet different statistical methods. So let me just describe this one, which combines the statistics and the algorithm. So a differentially private estimator, first I'm going to give you an analogy, then I'm going to give you the actual results. So you have a data set, we partition it up into slices, okay? We're going to imagine running a separate analysis in each slice. Computationally, that can be very efficient. We're going to use the bag of little bootstraps as an option. It's not necessary, but the reason for it is it scales up the smaller partition data set into the whole data set. So if we're going to estimate the mean, we can just average the means, no big deal. If we're going to estimate a variance, well, each of the variances within each of the partitions is going to be artificially larger just because it's a smaller data set. And so you can by hand scale that. But if you don't want to think about it, you can use the bag of little bootstraps and it will basically always work. Then we have an estimator. So you take the partition data and you run some analysis and you calculate some quantity of interest. Those use statistics types will be hilariously laughing despite the fact that you're on mute because of the sandwich estimator. Isn't that great? Okay. Then the sandwiches that come out too large, we censor. So you cut them up a little bit. Then we're going to average them. Now remember, what we'd really like is an average of these. that are private. These are all red because you can't see them. We're not allowed to disclose them. So we'd like to average these and get something that looks like a sandwich, but instead we have to average these, and we got something that looks like this. So that's biased. And then we add noise. We can see it, so it turns blue. But now it doesn't look at all like the average of these things. Okay, so that's my analogy. We're going to do a bias correction, get back to the sandwich, and we're going to do appropriate variance estimation. So let me just do this in math. So I put a little d here, and I'm going to put little d partition data sets there. I'm going to get rid of the bag of little bootstraps just to make it simple. And each of my estimators of each of my quantities of interest are going to be theta1 through theta5. And now I'm going to take censoring, averaging, and noise and put them all together into an equation quite like the one that you've seen before. So we're going to take the average of these guys, but we're going to censor them first. So it's the censored average of all these plus noise. Now, this is the same formula as for the mean, except instead of averaging over the n observations, now we're averaging over the p partitions. Now that has a tremendous advantage and a disadvantage. The tremendous advantage is that we don't have to come up with a different differentially private mechanism and a different statistical procedure for every statistical method out there. And there are an enormous number of them. There's a vast array of statistical methods, of course, a smaller number, but still a very large number of differentially private mechanisms for the different things that we would calculate. We would have to do an enormous array of things. However, what we're doing now is you calculate any quantity of interest you want with any statistical method you want, and then we're going to average the partitions, and we make the average differentially private. So that way it's generic. That's the idea here. So that's the advantage. The disadvantage is there's P here, partitions, rather than N observations. And since partitions are smaller than observations, we're going to add more noise. So we're going to pay for the fact that it's differentially private and generic. We're going to pay for the fact that it's generic by having that there. So hopefully we'll apply this to big data sets, and so that won't be much of an issue. We'll then, after that, do bias correction. Okay, and variance estimation. Okay, so now let me take that formula again and show you the bias correction. So this is the bias correction that we start with this, which is this number. This number is not a good number because it's a censored average and it's got noise added on to the end. The noise on average is 0, so maybe we could ignore that for now, but this is biased, right? If it's right, because it's censored. So let's see how we could correct that. This thing, so for starters, before we censor, let's take the theta hats, which I'm going to put here, theta hats of p for across the partitions. Those things are going to be normally distributed just by the central limit theorem. So they're going to be approximately normally distributed. So this distribution is the distribution of the p hats pretty much regardless of the statistical estimator. There's some regularity conditions on that. But regardless of the estimator, regardless of the quantity of interest, this thing is normal. What we want is the mean of these guys. We're not allowed to see that because they have to be censored. But this is what we want. This is our goal. That's the goal. So let's see what we actually get to see. So it gets censored. So the orange censored, see this orange up here, right? It gets this lambda is the chosen value that it gets censored at. And all of this area here gets piled up and put on here. So the orange distribution is the area under the curve and the spike here. Okay. The mean of the orange distribution is not the theta that we care about. It's moved over to the left because we've lopped off this piece of the distribution. So this is the thing we get to see. This is the thing that, or plus noise. This is the thing that we'd like. Okay, so how are we going to get back to the thing we like? Well, first let's label the area under here, which is alpha. It's just the integral from lambda up to infinity of that normal. And then we have this thing, which is defined in this way. So it's the weighted average of two things. One is the spike here, that's the second piece. And the second is theta t, which is the mean of the truncated piece. So this is statistical language for instead of the censored distribution, which also has the spike, the truncated distribution just has the distribution piece. Truncated would be if we lopped off the piece and threw those large values away. Theta t we can ignore because it's a function of all the other symbols on this page, but everything else we really have to pay attention to. Okay, so what do we have? Well, it turns out we have two equations normally we have censoring on both sides, so it's more complicated than this, but I think this will convey the point that we're trying to get across. There's two equations, but there's four unknowns, so it's sort of a bummer. But we haven't disclosed anything yet, so all's not lost. So we'll begin by disclosing the thing that we would disclose, which is up here. We're going to disclose this thing. That's what I'm going to put here, right? So by disclose, I mean show it to people. Okay. So we disclose that. When we disclose that, we get rid of one of the unknowns. So that's a good thing. We're going to need another one. So we disclose another one. We choose to disclose alpha. So once we disclose alpha, now we have two equations and we have two unknowns. So now we can solve for the answer with two equations and two unknowns. We can actually do it analytically. When we have censoring on the other side as well, we have to do it numerically, but it all seems to work fine. And so that's our bias correction. Okay. This very interestingly changes how you do differential privacy, because normally when you do differential privacy, you want to set lambda so there isn't too much bias. But now actually, since we're going to have a bias correction, we're okay with bias because we can get rid of it. So you might as well try to have censoring because then you can reduce the amount of noise necessary and you can correct the bias. So it's sort of an interesting consequence. So that gives us a point estimate that's approximately unbiased, but we also need uncertainty estimates. So let me show you how we calculate the variance. What we thought we could do was just disclose the variance because that's another function, that's another estimator, right? But it turns out that's not very helpful because we don't want a differentially private version of the variance of a thing that we don't have. That's the thing on the left here. Well, what we really want is the variance of the differentially private statistic. So the only way to calculate what we care about, which is the variance of the thing that comes out. So variance has to be calculated in post-processing. So what we do is we do it by simulation. So just my notation here to try to make it simple is we're going to try to create simulated values of the two quantities that we disclosed on the previous page. They are bivariate normally distributed from the central limit theorem. And the parameters of this distribution are all functions of the disclosed parameters. So we proved that was true. And then we run the bias correction. So this is a summary of the entire last page where you take these simulated values, you stick them in here, you run the bias correction and you get out these values. And then the standard error is just, you do this a whole lot of times and take the standard deviation of these simulated values. An interesting result of this whole thing is, well, as I said, the point of it is that the differentially private result is approximately unbiased, which is great. But in addition, usually when you correct bias in statistics, you pay for it in variance. But in this case, it turns out the variance is also lower. So if you do this procedure, you get an unbiased estimate approximately, and you get a lower variance. So it's good to have both. Okay, so now let me just show you how it works in practice. We've done it by lots and lots of simulations, so I'll give you a feel for it. I don't feel the need to tell you the specifics of how we did the simulations because we did it so many different ways just to give you a feel for it. So on the horizontal axis is the amount of censoring. It probably should be lambda, but I have it denominated in terms of alpha, which is the area under the curve that was lopped off. And over here, there's no censoring, and over here, there's lots of censoring. This is bias, the vertical axis. Over here, there's no bias. So with almost no area to the right, with almost nothing censored, there's almost no bias. But as censoring increases, the bias just gets bigger and bigger. In my academic department, the department administrator was asked to find out how long it was taking people to get their PhD. And so, not being a data analyst, she went back 10 years, took the cohort that started 10 years ago, and she figured out how long it took each of them to graduate. And then she reported the mean of those numbers. And I said, hey, what did you do with the people that are still here after 10 years? And she said, oh, I just put them in as 10, because they stay, cause that's right. So that's obviously biased, right? It's either biased or incredibly optimistic, so that's what this is. And this is our estimate, which of course is approximately unbiased, regardless of the value of alpha and regardless of the sample size. So I have the same thing here, regardless of the sample size and regardless of the amount of privacy that you wish to require of it. Each one of these, it stays at approximately 0. One other final point is this is the standard error of the differentially private estimate, which is the orange one. Below it is the standard error of our estimate, which is lower, right? So that's great, it's lower. And also there's 2 lines here, not one. They're almost on top of each other. One is the true standard error and the other is our standard error. So the thing that we're estimating is both lower than the other one, but it's also approximately correct, which is pretty essential. And then because I like the graph so much, I combine them all together just so I could pause and show them to you again, but there's really no purpose of this, this slide at all. Finally, let me just conclude. We're going to switch from a data sharing regime to a data access regime. I think places like the Google Cloud are going to provide specific servers that if you want my data, I'm going to give you a server. I can charge it back to you perhaps. And the server is going to have particular characteristics with differential privacy, with a specific privacy budget, and you're going to be able to analyze the data. And I think that's what we're going to share. We're not going to share data sets. Differential privacy protects individual privacy. It enables inference to a private database, not to the population, so it's not sufficient on its own. It's usually biased and does not come with uncertainty estimates, so it's really a problem on its own. And it fails to protect society from the wrong conclusions, really. So you don't want to share data and then only to have people have the wrong answer. This creates lots of noise. So the United States Census is making its data available in a differentially private way this year. And a lot of the people complaining are Democrats and Republicans who want the census to come out in a particular way. But a lot of the people that are complaining are the scientists, the social scientists who've been using the data and expecting it in a certain way. And now they have to change everything they learned in graduate school. So for inferential validity, a scientific statement is not one that is necessarily correct. It is one that comes with known statistical properties and valid uncertainty estimates. So our proposed algorithm is generic. It works for almost any statistical method or quantity of interest. So it should be attractive to these people who we've been pissing off. It's statistically unbiased and has lower variance. It needs a reasonable size n, although we've run it for data sets as small as a few thousand. It has valid uncertainty estimates, which is really good. It's pretty efficient computationally, and it solves political problems technologically. And there's some implementations in progress at Facebook and at Microsoft, and in a collaboration with us at Harvard and the Institute for Quantitative Social Science, and our OpenDP project, which I hope you will all join. And these are my awesome co-authors, and I'd be more than thrilled to interact with you guys and take any questions you might have.
Thank you, Gary, for this awesome talk. I guess we can have questions. Since I'm the co-author and I gave a talk on this variant, I don't have any questions to ask, but yeah.
So Kenneth has a good question. I don't know where how to use this, but it appeared there somewhere. Anyway, the number of partitions is an important consideration. We don't, if it's small, then we have to add more noise. So basically what you want it to be is as large as possible, subject to being able to get coherent estimates, right? Because if you only have one observation in each partition and you're estimating a regression coefficient, you're not going to get the answer. If you're trying to get, how do I, oh, there we go. Okay. Thank you for my, So you need enough observations within each partition to get a coherent estimate, to get a coherent standard error, things like that. Would it change based on the statistics you're considering? Yes, it would, because if you were interested in the mean, then you could have a partition of size 1 and everything would be fine. But for almost anything else, you would need a partition of another size. A fairly generic answer is, like, if you had 100 in a partition, you could do most things that you'd want. Now, but to be fair, I just averaged across all possible applications, which is absurd. You know, so, but just for the kinds of applications that most people would want to do, you know, I think, you know, of course, if the thing that you're interested in is the 157th coefficient on a regression with 2,000 parameters, then you need more than 100 observations. So that's a good question.
Any other questions for Gary?
I learned that oh, here we go. Do the partitions have to be non-overlapping? So that's interesting. They have to be non-overlapping for our variance estimates to work. It would be possible to adjust our variance estimates so that they could be overlapping. Let's see here. So is the limitation in the available budget of potential practical importance? I think it really is, because once it's used, you know, once it's used up, like, that's it, right? Like, if you really want to protect privacy to a specific level, then that's essential. Because one way to think about it is, suppose we're just estimating the mean, and we have a particular privacy budget, and you're allowed to run as many analyses as you want. Well, you just run, you know, 1,000,000, and you average them away, and then there's no privacy at all. So that's an essential feature of differential privacy, at least as taught to me by Aberdeen. I hate that feature, you know, but it really is. There's nothing else you can do about it. So if alpha is greater than 0, does that mean that lambda is less than the true mean? Things like strange things like that can happen in practice. Yeah, I mean, it is possible for lambda to be greater than, for alpha to be greater than 0.5, but we really have 2 lambdas, like the way the paper set up is lambda and minus lambda. You censor everything on the outside. You know, you can't have them cross. It doesn't make any sense. If there's no information in the middle, then you can't use that to infer the tails. So there is a balancing act here. We definitely want censoring because we can correct it, and that reduces the noise. But we don't want too much censoring, because then we've blown away all the information in the data. The bag of little bootstraps, it can use overlapping partitions, but it doesn't have to. And so we have it set up without overlapping partitions. But the bag of little bootstraps here is used within partitions. Within each of our partitions, the bag of little bootstraps is used. It's not necessary, but it could be chosen. So let's see, that was from Shannon, and Tom Stein is asking, how robust is the debiasing to model misspecification, i.e. if the data is not normal, but instead log normal or student t? So the particular assumption we're making is that we have enough observations for the central limit theorem to kick in. That's pretty robust. And so we can break any assumption. And so I would break that one by choosing a quantity of interest that had a bound, and most of the mass was right up against the bound. You know, but even so, after not that many observations, it becomes essentially normal. If there's misspecification in the original statistical procedure, then even without differential privacy, you would get bias. And after the correction, you know, I mean, I suppose it's possible that the bias you would have, you know, if you run a biased estimator, our bias correction, who knows, it might make things worse. I mean, it's not entirely clear. We'll get you back to what it is you intended to do, but I can't guarantee that what you intended to do was a good thing to begin with. Let's see. Brian Gibson says, curious about any general comments on this with respect to identifying ordinal statistics like the median or the percentile. So that's interesting. I think that our differentially private algorithm is the mean. It's not the median, and we'd have to do it differently for the mean. But however, our the statistic that we are taking the mean of could be a median and could be a percentile. You know, some things aren't going to work. Like if you did a maximum, you know, like using the data to, you know, using a histogram to find the maximum, using a sample to find the maximum isn't going to be a good plan, right? So some things clearly won't work, but that's the kind of thing where we're doing continuous statistics basically. So.
I had an elementary question. So you pointed out the limits of DP in terms of not being able to ask too many queries of the data. Are you saying that your scheme overcomes that? So like you're now free to do whatever analysis you want?
No. We still, there would still be an epsilon, and that would still be divvied up among researchers. They can run any statistical procedure they want, but for every one that they ran, they would have to choose how much of their allocated proportion of the total privacy budget that they would use. They might want to blow it all in one thing, or
oh, I see. I see. So some researcher would say, I want to do 10 experiments. You don't need to say what they are, and then they can choose they dial in a noise for each query that they want to make. Exactly.
That's right.
Yeah.
So they have to plan it out really carefully, right? Because what I'd really want. Sorry, go ahead.
Can you do this interactivity? So I like, then it's like a sequential, decision theory problem, right? I have some budget. I do a little exploratory work with half of my budget, and then I start exploiting a particular question.
So you can, but here's the evilness of differential privacy, it feels evil. So you could do that. So how would we do that? We would decide to spend presumably a small amount of the privacy budget just to look in a certain direction.
Yeah.
But if we're spending a small amount of the privacy budget, we get a telescope with not very good resolution. Mm-hmm. And we might not see the thing we're looking for. So maybe we would only do what you're suggesting if we're looking for what would be a really big thing, because then we might be able to spot it. So that's the first issue. The second issue is, yes, you could do it sequentially. However, if you run 3 analyses, you're allowed to take the results and combine them, and you'll get more precise estimates, right? Small standard errors. Mm-hmm. However, if you thought about it ahead of time, and you realized that that's what you wanted to do, if you knew that that's what you wanted to do, you could run all 3 for less of the privacy budget than revealing each of them in stages.
I see.
Right. So that's the real, it's like, oh, that really sucks. So because some smart aleck showed that if you release it in stages, that actually leaks some more of the privacy budget, and everything is accounted for in differential privacy. Every leak of privacy is accounted for. So, yeah. So you have to really make decisions. That's one reasonable way to go, but it has costs.
Interesting.
Yeah. So something that feels better for researchers is what we did with Facebook. Is we released this data set. With 17 trillion numbers in it. It is a differentially private data set. So the data set itself, the results of the queries, were the elements of the data set. And at that point, you can run as many analyses as you want on the data set, right? However, it has much more noise than if you were allowed to take the same epsilon that was devoted to the entire data set and ask your queries instead, right? So if on the other hand, you have exactly the same questions that is reflected in the structure of the data set, you're fine. But in all likelihood, you could have done better if you use the kind of system that we described today. But you have to decide ex ante. So having a differentially private data set feels better to existing researchers because that's sort of what they do all the time. Then they can run as many analyses as they want. However, they're running analyses on much more noisy data. So.
This is more of a comment rather than a question. Rather, at Google also, we are very much interested in designing algorithms for generating synthetic data sets with privacy. Not that anyone in the literature also has like very strong hold about it, but it's a very important active area of research.
I was actually thinking about that. If you need to design your experiments, I mean, if you're going to land on Mars, then you would actually build a simulator of Mars and do everything offline, and then you spend your one budget once, right? So, I mean, you could probably do something similar. If you think the data has a certain property, you'll build a simulator of it, test your inferential procedures, and then you run it live.
I think that's exactly right. So, but if you think about the way that you're thinking there, you're putting more and more ex ante, right? And then the question is, well, how good a simulated data set can we have?
Yeah.
And the answer is, you're not allowed to use the existing data set to create it. You know, so we just have to think about what it would be like. But you know, in some sense, we should always do that, right? And when data collection is expensive, we always do that. You know, I ran an experiment in Mexico where we randomly assigned hospitals and medicines and doctors to communities. It was an enormously expensive experiment. It was the largest public health experiment in history. So obviously, I thought really hard about everything we did before we did anything, right? But you know, if you have a survey and someone sends you the results, you know, the cost of running an analysis is essentially zero. So you run the first analysis before you even do the recodes. You know, you just sort of do it, and then you just sort of see, well, do we get anything? You know, and then you adjust. So it just changes your practices. You know. Yeah.
I guess we are reaching the end of the hour. So let's thank Gary again for his awesome talk. And in the email invite, in the invite for the talk, I had shared Gary's email address, and Gary told me that like you'd be really interested to talk to people. I encourage you, people who are interested, to kind of mail Gary. And
it would be fun if anybody was interested in anything. It would be great to follow up. I find you guys can hire people I could never hire, and I can hire people you could never hire. But when there's a flow of information back and forth, it makes us both better.
Thank you, Gary.
Thank you.
Great. Thanks, everybody. Take care.